はい。のとこですかね。ちょっと確認してもらえますか。
こっちお願いします。
大丈夫、大丈夫。
これはfor you or for me? You don't have, okay, you can take it.
I drink a little.
No, go ahead. No problem. のトライ。あれ？どっちですか？あ、これ。
2月22日月曜日、総括パターンの9回です。小野先生、どうぞ。
前回の研究会の後で将来どうなるかと心配をしたのですが、須田先生が非常に元気を取り戻してもらえて新しい展開を考えてください。喜んでいます。どうぞよろしくお願いします。
須田先生、どうぞ。まず最初に一言。はい、はい、どうぞ。
後で少し時間をいただいて、チャンさんの話の後で少し話をさせていただきたいと思います。で、今日急いでこういう会をやっていただいた方がいいと思いました理由はですね、ここでこの前、須田先生から薬標部の話をしました。でちょっと情報を集めたりしたんですよね。いろいろ見解もあったりするわけです。非常にその世の中はここで話している方向に猛スピードで動いている人がいましてですね。でどういうふうに動いているかというと、これもちょっと後で説明しますけども、 私はラインを引いて下と上とで、この研究は今上へ来てるんだという話で、しかしながらまだリニアにとどまってるで、それをノンリニアに行かなきゃいけない。そのための今その世界の動きがいろいろあるわけです。で、動きの中にはこの前ちょっとここで申しましたが、統計力学は従来の方法ではいけない、確実な方法ではいけないということをもう2年ぐらい前にで私に来て話をしようとおっしゃって、話をしたことがあります。でその時若干感じてたんですけども、今度はブラックショールの話をしましてですね、それで僕は前から思ってたことは無理があるなと思ってたんですけども、それに対していろんなコメントも、それからもう一つはですね、いやそのことを無視できないことがあるわけですけども、もう一つは何という人ですか、サテライトが上がりました。で、それを受けてらしいんですけども、名古屋の東京の牧島さんと連絡取ってる連中ですけども、今週の金曜日に話をすると、だから出てこいという話をしてますからね。で、それも似たような方向に来ているわけです。で、あらゆる方向でですね、一線を越えて進んでいるわけです。で、ここでも超えてはいるんだけれども、まだノンリニアな部分があまり進んでいない。で、それにはいろんなその課題も考えられることがありまして、それでこの際ですね、私もいつまで元気でおれるかわからなくて心配な状況があるわけですけど、急いで今の研究をそしてノンリニアの方向へ進めていただく必要があるんじゃないか、こういう思ったことが一つと。それから何度も来ておりまして、ちょうど、偶然ですけども、新しいノイズというレビ分解で糸分解がミスしている部分が非常に大事なことが分かってきて、でそれに対して非線形なものを考えなきゃいけない。そうするとどうしても繰り込みみたいなことがいるわけですからね。で、当面の今のいろいろな問題に、なっている部分がクローズアップされてきようとしている。で、そんなこともちょっと聞いていただくことがいいんじゃないかなと。で、一つはですね、この研究がもっと促進されることを願っているわけでありますけども、願っているだけじゃなくて、その方向にも準備はできているので、スタートラインは遠くに切ってあるわけですから、急いで進めていただきたいなと。で、旗振りに来たというのが本音ですけども、でそれどうすればそういうことになるかということをですね、少し後で話をさせていただきたいと思っております。で、もう一度前に申しましたノルさんが先生言っていることを繰り返しますけども、超一流でなければ研究はやめてしまえと、これは真理で、もう勉強してるなんていう時間ではない。で、やめてしまえと言われないようにですね、頑張ってほしいなと思うんですけども、実はそれは望みだけではなくて、そういうことができる状況にあるというふうに私は思っておりますので、これはお世辞で言ってるわけです。で、こういう方向の研究が促進されることを望みますし、一つのポイントはですね、リノーマリゼーションがノンリニアになりますから、リノーマリゼーションです。で、これちょっと後で話しますけども、ちょうどチャンさんが取り合ってることがありまして、新しいノイズであることと、そのリノーマリゼーションの問題がありますので、ちょっと話を聞いていただいてですね、後から私は少し、補足といいますか、現状をいろいろ踏まえながら話をさせていただきたいと思っております。そういうことです。
ありがとうございます。
皆さんおはようございます。これは私の1ヶ月の研究報告です。でも今、everyone know my 私の日本語まだ上手です。それから英語も使います。今日today my title is Nonlinear Functional of Space Noise. because in my previous paper I do a little about the functional space noise lambda, the intensity lambda. But in my previous paper I assumed that lambda and jump U, the span of lattice type, is one-to-one correspondence. But now we not have this assumption, so we use another way to think about the lambda. So we think about lambda, the space noise directly. So we come to the lambda and P dash lambda. So now we come to the nonlinear function of the lambda, P dash lambda. So I will give some introduction, and second we will go to the chapter 1 is the linear function, and the next is the generalized linear functional, and the next is the polynomial. And the final 2 points I still work on it, so not very complete. And first in the introduction, we can see the last page. We can see the reference 6. We have motivated by the Levy's paper in the 1934. We have this paper. We can know in the noise we have 3 kinds of noise. One is Gaussian noise, that's white noise, P dot T, and the proton noise, P dot T. So we know that both noise is depend on the time variable. And second, we want to know the space noise is depend on lambda. So because we know the convergence is from the law of probability, so we know it's hard to compute. So we focus on the characteristic function to know the property of P dash lambda. And if we see the C cos C, we can see the cos C is in the nuclear space E, and we can form this kind of exponential integral. So the the nuclear function is dense in the L2. And next we will start from the linear function of P dash lambda. And in the point 3 and point 4, we will introduce a triple, like a Diophant triple, H1, H1, 1, H1 minus 1. And we reduce a new space noise, the triple. The triple is like the space. The space is the R. Why we call it R? Because in the German, we know the Raum is the space. In German, the RAUN means the space. So we use the first letter to represent the space. We can introduce the space R1 minus 1 as of the general function, linear functional, where the P dash lambda lives in the R1 minus 1. So we will form a sequence Rn to be the P dash lambda of the degree n. And finally, we can investigate the P dash lambda polynomial and to know some of the fraction power distribution is the stable process to relate it. So in the section 1, we have the linear function of P dash lambda. We have this kind of form. F lambda, P dash lambda, this kind of integral. And we know, as I mentioned about, it's a limit in probability distribution. So we hard to compute it because the topology is weak. So we use the correlative function C cos C to know the property. So first, we want to know some Haykin's magnetic the expectations property. So we have to think about the random variable x and y. And when x and y is independent, they have the kernel function g f lambda and g lambda. the product of 2 is equal to 0. So we prove it by the characteristic function. So when we compute it, we can find it can be separate, and we separate the domain to the 4 parts. One is f and g equal to 0. The second is f not equal to 0, and the third is g not equal to 0, and the cycle, the last is both not equal to 0. So we can know the characteristic function in the plus can be separated to the product. And next we try to differentiate it, so we can know it can be found the f lambda product g lambda can be equal to 0. And converse is vice versa. So from the theory, we can have this corollary. It's the P1 and P2, they are the polynomial. The polynomial, if they are independent, P1 and P2 are independent. So we can know the function of P1 and function of P2 also independent. And next, we will introduce some IID system, like the Fn, P dash lambda, and the support of Fn's. They are mutual disjoint. So it's very important for us to investigate. So we have this kind of lemma. That is, the kernel function is different. When the kernel function f lambda and g lambda are not different in some interval of lambda. So we can know the both random variables have a different distribution. And we prove it also from the characteristic function. So we can see the compute can give the complete proof. So we come to the next point. Second point is generalized linear function. As we, in the point 1, we have the linear function p dash lambda. But not just linear function or p dash lambda. We can investigate by the characteristic function and some of the hacking mechanics, so to know the property of the p dash lambda. But now we have come to the generalized part. So because we mentioned about we have to induce a triple R1, R11, R1 minus 1, this kind of Gilfan triple. So we have to definition the norm of the R1. So because we know the F1 norm have this Cauchy inequality can less than the F2 norm. So we can, from this inequality, we can know the random variable x has the mean and variance. They are finite. So if we can define the R1, we can also try to define R11 and R1 minus 1. Because the R11 is defined, so we can use the dual of the R11 to introduce R1 minus 1. And we have to show the P dash lambda can live in the R1 minus 1. So when we write the P dash lambda as this integral form from 0 to 1, and it can be a product of delta function to P dash function. So we can know P dash lambda is very rigorously defined in the Hilbert space R1 minus 1. So if we want to know the polynomial of P dash lambda, we have to establish the triple R1, R11, and R1 minus 1. So we can know the more high degree polynomial to involve with the Gilfan triple. So because we want to compute the polynomial, we have to choose one polynomial. In the Gaussian case, we know the polynomial of orthogonal polynomial is Hermite polynomial. It can be orthogonal in the Gaussian space. But in our case, the Poisson system, space system, space noise, we have to choose another polynomial to compute it. So we choose the Poisson-Charlier polynomial to compute the p dash lambda. And we can use the generating function like this gx w lambda to compute the orthogonal polynomial in the R1 minus 1. So next we come to a theory. The theory is talk about the lambda is not the ordinary function. The p dash lambda is not ordinary function because the lambda can exist as the stochastic system. And because the proof we know is similar to the previous theory, so we emit it here. So we now can consider the CC defined as a general system that has independent value at every point lambda. We can define the linear system f lambda product p dash lambda and integral d lambda. So when the f is in the L1, from 0 to infinity, we can know the CF can be write as this kind of exploitation taking. So we can get the f lambda integral, maybe the moment 1. And when f is equal to L1 intersection L2, we can know the second moment can be written as this form. And now if we restrict the zero integral from 0 to infinity to 0 to 1, so we can know latter property. So we have the following proposition. The proposition is similar to what I just said, because all the moments of p dash f will exist. So we know the nonlinear term of the polynomial p dash lambda when f equal to the LP 0 to infinity. When p greater than 0, we know the first is expectation 0 to 1. F lambda p dash lambda, it will be equal to 0 to 1 f lambda t lambda. And the second we can compute it from with derivative of the corrective function by phi 0. So we can know the second moment will be written as this form. So the next important second to the point is the generalized function of p dash lambda. What we mentioned of linear function, but now we go to the generalized function of p dash lambda. So we should establish the decomposition Rn and Rn minus n. So we have to know the direct product to have the decomposition. So when R plus this space is the test function and R minus is the space of generalized function of p dash lambda, we can form this kind of the triple. So the basic idea of the decomposition of R plus minus is similar to the Gaussian case, like the reference 7. The reference 7 is the Professor Hita and Professor Sisi. They both write a book, this lecture on white noise function. In the book, chapter 2, we can have the similar idea in the Gaussian case. That's the Hn minus n, Hn. So that's similar important idea to introduce this kind of triple. However, some significant parts should be taken into account. So we have two ways of application. One is the Poisson process may be written as PT lambda, an intensity lambda, with this kind of lambda. From its distribution, we may consider T and lambda will play a similar role, but not quite. What's the similar role? The similar role is T and lambda may be a dual pair, but we know the domain of T and the domain of lambda is different because T is from finite infinity to infinity, but lambda is from 0 to infinity. So even they have dual pair property, but not quite very the same role, just a similar role. For a more deep consider, we can introduce the two parameters, have the stochastic process, and think of the role played by each parameter together with some hidden relation between them. And the second application and remark, we can come to, we know maybe in the future have a lot of application about our theory. One is concerned with the structure of the P dash lambda that can create the fraction power distribution, like I just mentioned about the stable process. Briefly speaking, the parameter lambda or P dash lambda runs through 0 to infinity in a homogeneous manner. Hence, the dilation group is naturally concerned with, like I just speak here 2 weeks ago. So we can know the AZ1B. This kind of dilation group can action on the P dash lambda. The fact directs us to consider the fraction power density of lambda with the note that lambda and span U have the relative sympathy. So we can state the essential difference between the space noise P dash lambda and the Poisson noise P dot T. Both of the general random system have the independent value at each point. So every point. So the difference between them comes from the different type of the domain in the when the parameter runs. And we have a lot of work to do the renormalize or the generalize of the polynomial P dash lambda. So I have to accept. In Japanese we call it ishokebe to do it. So I have a lot of work to do and wish everyone can enjoy this kind of P dash lambda. So thank you very much.
数学会の講演みたいになっちゃったんですけど、リノーマリゼーションのところをもう一遍出してみてください。リノーマリゼーション。シャリエポリノミアル。リノーマリゼーションのところ。next page. 그具体的な式を出さなかったんですけどもね、元はガウスの